In this tutorial, the distributed magnetic field and the inductance are solved when the current is applied to the coil with core. We can visually understand the direction and magnitude of the magnetic field vector, magnetic flux density vector, current density direction, and so on. A new project is created first. Create a new project. Click the File tab and select New Project. Set up the analysis space as follows. Model unit millimeter. Analysis space 3D. Click OK button. The initial setting has been done. Let's create a cylinder for a core. On the Model tab, click Solid Body and select Cylinder. Designate the center. In the Parameter Input dialog box, enter center, X0, Y0, Z0, and click Next button. Specify the radius. Enter radius, 8 in the Parameter dialog box and click Next button. Specify the height. Enter height, 30 in the Parameter Input dialog box and click Complete button. Click Exit button in the Parameter Input dialog box and exit. A cylinder for a core has been created. We create a cross-section of coil. First, we change the drawing plane. On the Model tab, click Reverse Triangle under Drawing Plane. Click ZX Plane on the submenu. Draw a rectangle sheet body. On the Model tab, click Sheet Body and click Rectangle, specify length. Designate the start point. In the Parameter Input dialog box, enter start point, X9, Y0, Z5. Click Next button. Specify the width. Enter width, 20, and click Next button. Specify the height. In the Parameter Input dialog box, enter height, 3. Click Complete button. Click Exit button in the Parameter Input dialog box and exit. The cross-section of coil has been created. Rotate the cross-section of the coil that was created in the preceding session and create a coil. On the Model tab, press Reverse Triangle at the side of Extrude. Then click Revolve on the submenu. On the modeling window, bring the mouse cursor to the cross-sectional body of the coil, highlight it and left-click to select. Click Next button in the Revolve dialog box. Specify the point on the rotation axis. In the Parameter Input dialog box, enter point on rotation axis, X0, Y0, Z0, and click Next button. Specify the direction vector of the rotation axis. In the Parameter Input dialog box, enter vector of rotation axis, X0, Y0, Z1, and click Next button. Specify the rotation angle. In the Parameter Input dialog box, enter rotation angle, 360, and click Complete button. A coil has been created. Model creation has been completed. We set the analysis conditions. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog will show up. On the Solver tab, select Magnetic Analysis Gauss. Go to the Magnetic Analysis tab. Confirm that the analysis type is Static Analysis. Click Mesh tab and set as follows. Deselect, set the general mesh size automatically. And enter 2 in General Mesh Size and click OK button. The analysis conditions have been set. We assign names to the body attributes and the material properties. Highlight the body of the coil and click to select. On the right-click menu, click Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Coil, and click Edit Data. In the Edit Body Attribute, Coil dialog box, go to the Current tab. Enter the following setting. Current, 1 ampere. Turns, 100. Direction, loop coil/magnetic field direction. Magnetic field vector, X0, Y0, Z1. Then click OK button. In the Body Attribute/Material Property Setting dialog box, enter Material Name, CU, and click Edit Data. In the Edit Material Property, CU, dialog box, select Electric Conductivity tab and enter as follows. Conductivity type, conductor. Conductivity, 6 × 10⁷ power Siemens/meter. And click OK button. Then click OK button in the Body Attribute/Material Property Setting dialog box and exit. Next, assign a name to the core. Highlight the body of the core and click to select. On the right-click menu, click Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Core. Enter Material Name, Core, and click Edit Data. In the Edit Material Property Core dialog box, select Permeability tab and enter as follows. Material type, soft magnetic material. Relative permeability, 5000. Click OK button. Then click OK button in the Body Attribute/Material Property Setting dialog box and exit. The body attributes and the material properties have been set. Run the mesher and the solver. On the Model tab, click Run Mesher/Solver. The calculation will start. The Calculation Finished dialog box will show up when the calculation finishes. Select both Fields and Tables and click Show button. The table will show up. The calculation results are available in various formats. Check the calculated values. Open the Inductance tab of the table and you can see that the coil inductance has been calculated to be approximately 540 microhenries. Closing the table, the screen will change to Results window, and the meshing result will show up. Let's see the vectors of magnetic flux density. On the Results tab, initial setting of the field drop-down list is Magnetic Flux Density. Click Element Vector. The vector diagram of magnetic flux density will show up. The magnetic flux density can be seen circulating along the circumferential direction of the coil cylinder. Let's see the vectors of electric current. With Element Vector activated, go to the Results tab and select Current Density on the drop-down list at Field. The vector diagram of current will show up. You can check the current density distribution around the inside of the coil. Unlike magnetic flux density, current density is distributed only inside the conductor. Finally, save the project. Click the File tab and select Save Project As. Enter the file name and the location in the Save As dialog box, and save it. Saving allows you to launch Femtet at a later date, open the project, and review the model and analysis results. That's it for the magnetic static analysis tutorial video. See the tutorial topics in the Femtet help for more information. Thank you for watching until the end.